Welcome back, everyone. In this video, we're going to wrap up our discussion of Gauss's law by looking at a few more example problems. So before we do that, one thing that's important to talk about is the idea of conductors and insulators. And here are some just basic ideas to keep in mind. The first thing is that if you have an insulator, once you distribute charge on it, it's typically going to stay put. And that's because there's really no inclination for the charge to move. That only happens on a conductor where you have a material like a metal that might allow for electrons to move around. And if the charge is spread uniformly, then you can use the relationship rho equals Q over V. But this is only for an insulator. If you have a conductor, life is a little bit different. So Q and V would be the charge and volume of the insulator, and it's very important to point out that this is only if charge is spread uniformly. If there's a charge distribution that goes as a function of R, well then this just simply isn't true. And we'll see how to deal with that later. But the simple answer is that you can write rho is equal to dq dV. And that's what we have right here. Okay? And for a sphere, dV is equal to 4 pi r squared dr. So that means that dq is then equal to rho times 4 pi r squared dr. And typically rho will be a function of r, so then you're able to go from there. And when using Gauss's law, we would typically see the integral of E dot dA is equal to charge enclosed over epsilon naught. But the charge enclosed is really going to be the integral of dq. So we would integrate dq from one limit to another, sometimes from 0 to little r, or 0 to big R, so on and so forth. And dq, of course, could be this expression of rho 4 pi r squared dr, and that will convert it into the correct variables. Okay, now a word about conductors. If you put charge onto a solid conductor, it will immediately move to the outside surface, because like charges repel, and the furthest away that these charges can get is if they're on the surface. So that would be if I had a sphere that had charge spread out like so. Now it doesn't really make sense to talk about a charge density for this because there's no charge within the volume. Instead, we would talk about a surface charge density, which could be Q over 4 pi r squared, where r is the radius of that sphere. It could be a cylinder as well, in which case the surface area would be different. And so the exact distribution depends on the shape of the surface. It's not always even. What we'll see in the next unit is that if I have a spike, that charge tends to clump at the point. And this is related to energy, and we'll need to discuss that a little bit later on. But the next point is extremely important. Because all the charge goes to the outside surface, the electric field inside a conductor is 0. So if I was going to draw a Gaussian surface inside my conductor, that would have a Q enclosed of 0. And it doesn't matter where that surface is, those all have Q enclosed of 0, because there's no charge inside of that Gaussian surface. So this is, I guess you could call it a theorem or an axiom, but this is extremely important, that the electric field inside a conductor is 0. And as a matter of fact, charge will move in order to make this happen. For example, let's say that I have a point charge right here with positive Q, and it's surrounded by some sort of a shell. And I haven't drawn the entire shell, but think of like a ring or a torus or just some sort of a thin sphere that has sort of an inner and an outer radius. Now if I drew a portion of my Gaussian surface kind of like this, I need to make sure, and maybe it extends like this, I need to make sure that Q enclosed is equal to 0. In order for this to be achieved, charge will move so that there's charge equal to negative Q on the inner surface and positive Q on the outer surface. And again, this is only because of the presence of this plus Q right there. So this is a very important point, that the electric field inside a conductor is 0, and you can actually start from that when solving problems. And we'll say it again here for good measure. The electric field inside a conductor is 0. Okay, also we mentioned this in the previous video, but the electric field at the surface is perpendicular to the surface. And this has a lot to do with that Ghostbusters rule that we can't have these field lines crossing. But another deeper way to think about this is that the surface is going to be at the same energy or potential. And we'll get more into this in the next unit. Okay, so here's an example. Let's find the electric field inside a charged non-conducting cylinder with a constant density charge distribution. Now we don't know if that's a linear distribution or a volume distribution, but now we're talking about a cylinder that is non-zero in size. It's not a wire, it's an actual cylinder with some sort of a thickness to it. And let's just say that it has a radius of big R. So what we can do is we can draw a Gaussian surface, which is another cylinder that we place inside. And this Gaussian surface will have a radius of little r. And so, of course, if we want to apply Gauss's law, we have to use the integral of E dot dA is equal to Q enclosed over epsilon naught. Now, like we've said before, the electric field will not be coming out of the end caps in this example. Okay, so the electric field will just be going out straight. And again, that is the Ghostbusters rule, or the fact that the electric field only has one value at any position in space. And we're not going to deal with the ends right now. We're going to pretend like it's a long charged non-conducting cylinder. And then we can just look at a sample of it that has a length L. And for convenience, we can also make the Gaussian surface have a length of L. So that means that again, dA is going out, E is going out, so E times the integral of dA, as we've done before, is equal to Q enclosed over epsilon naught. Okay, so how do we find Q enclosed? Well, we're going to use a volume density and say that's equal to the total charge over the total volume, and that would be the purple cylinder. So maybe I'll just write that in purple to emphasize this. Okay, so the Q of the purple one and V of purple. But that's also equal to Q over V that is enclosed by the Gaussian surface. So we have kind of a ratio. And the way that we're able to do this is that we have constant density. So the two ratios are equal. Now this means that we can write the charge enclosed, Q enclosed, as equal to Q times V enclosed over V total. Okay? And so Q, we're going to leave like that. And V enclosed is going to be the area of the end cap, so pi little r squared times L, and then the total volume will be pi big R squared times L. Okay? So that's Q enclosed. We put that, and those cancel by the way, put that into Gauss's law, so we get Q little r squared over big R squared. And so then on the left side, E times the integral of dA is just going to be equal to E times 2 pi little r L. Now why is it 2 pi little r L? Because the surface area of this Gaussian cylinder is 2 pi r L. And that's going to be equal to q r squared over big R squared. One of those r's will cancel, and we're going to get the electric field is QR over 2 pi, oops, I forgot my epsilon naught. 2 pi epsilon naught big R squared times L. And the last thing that we can do is, if we want, we can invent a linear charge density, and that's just the way that we can write Q over L. So we could write this as lambda little r over 2 pi epsilon naught big R squared. And it turns out that when little r is greater than or equal to big R, this reduces to what we found for a line of charge. And so it works exactly the same way. Okay, so next we're going to find the electric field inside a charged non-conducting sphere of charge density rho. Okay, so that means that we have a sphere that has charge density rho, which is Q over the entire volume, or like we did last time, Q enclosed over V enclosed. So we'll do this kind of quick, but if we set up a Gaussian surface, we can find Q enclosed here as Q times V enclosed over V total. And I know that color isn't the best, so I'll just write it like this. So V enclosed, it's going to be 4/3 pi little r cubed, so that'll be little r. And the sphere itself is, let's call it big R, so that'd be 4/3 pi big R cubed for the volume of the big sphere. So that means that Q enclosed is just going to be big Q little r cubed over big R cubed. Okay, Gauss's law says the integral of E dot dA is Q enclosed over epsilon naught. And on the left side, we're going to turn that immediately into E times 4 pi r squared. We've done that enough that that's okay, and that's little r. It's not a dot product, just multiplying. Q enclosed, therefore, will be Q r cubed, and then we have epsilon naught big R cubed. So the r squared cancels, and we have an electric field which is equal to Q times little r over 4 pi epsilon naught big R cubed. And that was fast. That was really fast, wasn't it? So if we graph this, we notice that up until little r equal to big R, we have a linear relationship. If I pull out all those constants, whoops, I hit the wrong button. We pull out all those constants, it's just linear, okay? And then when little r is greater than big R, Q enclosed is just the total charge Q of the sphere, and so we just get basically Q over 4 pi epsilon naught big R, little r squared. Okay, so it's proportional to 1 over little r squared here, and proportional to r right there. Now there's a disconnect at the top, and that's because you're going from charge to no charge, so it's not differentiable, but it is continuous, because if you plug in that little r is equal to big R, you're going to get Q over 4 pi epsilon naught big R squared. So it is a continuous function, it's just not differentiable at the edge. And that's okay, but we'll talk more about how to deal with that next time. Now one last thing is that also on the same YouTube channel where you're finding these videos, I've done a slightly more complicated derivation of Gauss's law for a charge distribution. So I highly encourage you to check that out, and I'll also try to link it in the comments for this video. Okay, so next time we'll start talking about electric potential and electric potential energy.